In this video, I want to look at position differences. All right, so I have 2 points in time, some initial time, some final time, and I want to know what is the change in position, delta x, I'm still working in one dimension, over this time interval. Well, delta x then is the final position minus the initial position, and that's equal to the position function evaluated at the final time minus the position function evaluated at the initial time. And there we have this magic again. I apply the fundamental theorem of calculus, and this gives me the integral from the initial time to the final time of the velocity function over that interval, because the position function is the antiderivative of the velocity function. I can write that relationship down. Okay, so we saw that same sort of thing with velocity differences. So let's do an example. We'll do a more interesting one this time. Let's say I have a velocity function that's equal to 4 times e to the minus 2t. So it's exponentially decaying. It starts with a velocity of 4 and exponentially decays at this rate. And I want to ask, how far does it get? How far does the object that has this velocity function, how far does it get? I mean, like in forever. So what does that mean? That means, okay, so my initial time I'm going to say is 0, and my final time is going to be infinity. It gets forever. Okay, so you might think that this is pretty bizarre. This, in fact, comes from a homework problem that I assign in the in Physics 2. So how far does this get? Okay, well, I need to then calculate the integral. So delta x, sorry, then is the integral between these two times, 0 to infinity, of my velocity function, which is 4e to the minus 2t dt. This is a definite integral that I hope you know the answer to. And so this is equal to 4. I pull out the 4, and then that integral from 0 to infinity is just equal to 1/2. And so the change in position is equal to 2 meters. The expression I'm using is the definite integral of e to the minus at from 0 to infinity is just equal to 1 over a, if you don't remember what that is, but that's a very handy expression to know. So interestingly, so in this problem, I don't going to get there yet. In this problem, the velocity never goes to 0. It starts at 4, and it just decays, and it is always positive from t is equal to 0 to 2 is equal to infinity. However, the position difference is finite. The area under this curve, even though it has contributions to infinity, the area is a finite value. And so the total, even though it never really stops, it just gets slower and slower, and it asymptotically approaches a 2-meter position difference. Okay, so again, position differences using the fundamental theorem of calculus again. I want to look at the graphical representation of this in a little more detail here. Okay, so now I'm going to start with an acceleration and see how the velocity and the position functions, what they look like, qualitatively and quantitatively. So again, I'm going to start with a constant acceleration during this first. I have my time intervals down here. This first time interval of 1 second of 2 meters per second squared. So I can calculate the change in velocity over this interval, which is the area under that curve, which is just 2 meters per second. So the change in velocity is 2 meters per second. We're going to assume both our initial v0 is our initial position and our initial velocity is equal to 0. So our change in velocity is 2 meters per second, so it goes from 0 to 2. And it goes in a straight line because the slope of my velocity is constant throughout this region. Okay, so now with my velocity over this region, I can calculate the change in position, which is the integral of the velocity function, which is graphically represented by the area underneath that curve. And so the area of that curve is, under that curve is just the area of a triangle, 1/2 the base, which is 1 second, times the height, which is 2 meters per second, which gives me then change in position of 1 meter. I should use a different color, but okay. And so the initial position is 0. The final position is 1 meter. Now it's a parabola in this case because the position is changing faster at 1 second and it changes very slowly near 0 seconds. So I've got a sort of a parabola going from 0 to 1. Okay. So let's do another one. I'm going to say in the next region from t is equal to 1 to 2 seconds, my acceleration is 0 over this region. So then I can calculate the delta v, which is the area under that curve, which is also 0, so the velocity is constant. I really kind of wanted to use green for this, so I'm going to switch over to green. Green, so green. And so here, so since the acceleration is 0, the velocity is not changing, and so the velocity is just a straight line. The position is certainly changing because the change in position is the area or the integral of this curve, which is the area under the curve, which for 1 to 2 seconds is now is just the base times the height of that rectangle. The base is 1 second, the height is 2 meters per second, and so the change in position is 2 meters. So that means the curve is going from 0 to 3 meters in this time interval, and it does it in a straight line. If I could draw a straight line, I would show that it's changing from 1 to 3 meters in a straight line. So again, the area under this curve is the change in the position function. Okay, so now I'm going to take my acceleration to a negative 2 meters per second squared. I can calculate my change in velocity, which is now a negative 2 meters per second. The area under this negative function is negative. And so my change in function is 2 meters per second. So that's telling me my velocity is going from 2 meters per second back down to 0. And it's doing in a straight line. The velocity has the same negative slope throughout, which is equal to 2 meters per second squared. Okay, so I can calculate the change in position again, which is the area under that curve, which is just the area of that triangle, which is 1/2 the base, which is 1, times the height, which is 2, which is then again 2 meters per second, base of 1 second, and the area is 1 meter. Positive 1 meter. So it goes further to a higher value of x, even further, going between 2 and 3. So here it starts, it's changing much faster near 2 seconds, and at 3 seconds it's barely changing at all, so I got another sort of parabola that looks like that. So I want you to pay attention to this. Here, this is important. In this region, the acceleration is negative. Okay, fine. The velocity is positive and decreasing because the acceleration is negative. Because the velocity is still positive over this region, the area is positive, and so the position continues to increase even though the acceleration is negative. And so the acceleration can be negative and the position can still increase in value as long as the negative acceleration is simply decreasing a positive velocity to a lower positive value. Okay, so that's important to spend some time to make sure you can get your head around that. Okay, so let's finally continue where we're increase our negative acceleration to 4 meters per second squared. Our change in velocity is going to be the area under that, which is negative 4 meters per second. Okay, and it's going to change it in a straight line, so it goes from 0 to 4 meters per second in that interval in a straight line. And so The velocity curve looks like that. I can now calculate the change in position, which is the area under this curve, which is now negative. And the base of the area of that triangle, the base is still 1, the height is now 4, so a change in position of 2 meters. And so negative 2 in this case. Now we do actually have a negative change in position. So my position is now decreasing in value, going from 4 to 2. And it starts changing not very much at the beginning and changing a lot at the end. And so I've got a parabola going from 4 to 2. Okay, so I've spent some time going between the acceleration, velocity, and position graphically here, using the relationship between velocity and position differences to be quantitative about the changes in how those changes are represented on our graphs.